So how fast, assume it's a one-dimensional problem, in other words, it's only going to stay along a line. What are the velocities of the two masses after a one-dimensional, perfectly elastic collision? And I'm going to pause the video. And hopefully remember to turn it back. All right, any questions? All right, the last two bits with momentum. I say two, there might be more. Two of the last bits. Now this one's slightly off, unfortunately. You can buy better ones for less. I assume most of you are familiar with this. It goes by many names. Newton's cradle, I think, is the most common one, but unfortunately, one of the plastic threads holding it in place is slightly off, and so they're not lined up as nicely as they should be. But the question is, if I pull two back, why do two go? If I pull one back, why does one go? And so forth. So let's take a look at the scenarios. First, we'll consider conservation of momentum. And I'm going to simplify it down to, I have a 1 kilogram ball. It is massive. Heading to the right at, let's go with 4 meters per second. And over here at rest, I have 4 balls. All the balls are the same mass, so V initial equals 0 meters per second. And so let's take a look at the various scenarios. Scenario number 1 is one comes in and just stops. So this is the initial, final, so my initial momentum here, what is my initial momentum? Oh, Andre, I think you flashed up the, for what? All right. So afterwards, it needs to be 4 kilogram meters per second. So if they all stopped here, what's my momentum afterwards here? I assume the head shaking of Ajay was indicating the answer. All right. So right off the bat, it doesn't require any additional work whatsoever. This just is not going to happen. Not in a closed system. In an open system, it might, for instance, if those balls were stacked up against the wall and they threw this one at it, it is possible. Or if it's putty and the rest are stuck up against the wall. So scenario number 2, still this initial is coming in, and then afterwards, 4 stays still and 1 shoots onwards. So what I want us to do is figure out what is the velocity of that one ball over here. Well, I know these are at rest, so V final equals 0 meters per second for the 4 that stay behind, and then 1 shoots off at some velocity V. I am assuming that the momentum is conserved. It's a collision. And so I have 4 is equal to 1 times V. This 4 right here comes from the total momentum initially. This is P initial equals P final. And so therefore, P final is 4 meters per second. So if one comes in at 4 meters per second and then one goes out at 4 meters per second, momentum is conserved. Scenario number 2 is I have 3 stay behind and I have 2 shooting off at some speed v. My initial momentum is still 4. My final momentum is 2 times v final because I have 2 kilograms shooting off to the right. So v final is 2 meters per second. Momentum is still conserved. So if the one comes in at 4 meters per second, collides, and then shoot off at 2 meters per second, momentum is conserved. Scenario number 3, 2 stay behind, and 3 shoot off to the right. My initial momentum is equal to my final momentum. And momentum is still conserved. And then going through the next scenario, if 4 go shooting off, how fast do they need to go in order to preserve conservation of momentum? Final velocity, 1 meter per second. Then 1, 2. And then if 5 shoot off, so it collides and then the whole group moves. V final is 0.8 meters per second. So other than the very first scenario, which I probably shouldn't have put up there, but other than that very first scenario, momentum is conserved in all 5 of these other cases. But nature seems to pick the first one. So let's explore that. Let's bring in kinetic energy. What is the initial kinetic energy of the system? All of you know the formula.
T.
How'd you get 2?
Half of the mass is T and then the velocity is 0. I was looking at the 4 kg mass. 4 kg meters per second.
Oh, that's the initial momentum. So we got a 1 kilogram mass going at 4 meters per second. What's its momentum? What's its kinetic energy? I want the number.
8.
There we go. 8 what?
8 joules.
Joules. All right, so it's 8 joules. Technically, we would find the kinetic energy of this plus the kinetic energy of those. What's the kinetic energy of these?
0.
So 8 joules plus 0 joules, 8 joules. So we have a total initial kinetic energy of 8 joules. And now let's take a look at the kinetic energy in each of these other cases. Now, I know all the ones that aren't moving have kinetic energy of 0, and so we'll just concentrate on the other parts. So this is 1/2 times 5 times 0.8 squared. Because I have 5 kilograms moving to the right at 0.8 meters per second. .6? 1.6 joules. So we start with 8 joules of energy, we end up with the 1.6 joules of energy. This is a perfectly inelastic collision, by the way. The next one here, we got 1/2 times, I have 4 kilograms now moving at 1 meter per second. 2 joules. That one I can do. Then I have 1/2 times, I now have 3 kilograms moving at basically 4/3 squared. So 2.6 repeating. Say it again.
2.535.
Yeah, something's off. Did you use 1.3? Okay. Instead of 1.3 repeating?
Oh, no, I just put 1.3, that's not bad.
That's what I got.
Yeah, 2.6.
Alright. So we still have an energy loss each time. Now this next one right here, we have 1/2 times my mass, and now I have 2 kilograms moving to the right at 2 meters per second. I'm at 4 joules. And then the first scenario right here, once we ignore the one that's impossible, that's not gonna happen, 1/2 times 1 times 4 squared equals 8 joules. You can go through the same scenario with 2, starting with 2 kilograms moving to the right. The one which comes closest to preserving the kinetic energy is the one that is the scenario that seems to show up. So it comes close to simulating a perfectly elastic collision. It helps. You basically need to wind up better, but you also need objects here that aren't going to flex much. I guess to preserve kinetic energy, you need things that either, well, particularly elastic. I'm trying to think, if you drop the tennis ball and a steel ball onto a hard surface, I suspect the steel ball's gonna, if the surface is hard enough, the steel ball will bounce up higher than the tennis ball, but I don't know. But for steel on steel, yep. So I at least wanted to run through that. The next one's gonna be more problem-oriented, of combining stuff that we've done from chapter 7 and then chapter 8. So questions on this before I erase it? More level than that. What we do? So we have, so 5 kilograms, 10 kilograms. Meters. Spring constant is, we'll make this 20 newtons per meter. That's a lowercase k. When the 5 and the 10 collide, let's solve it twice. So perfectly inelastic collision, and then we'll solve the perfectly elastic collision. And the question is, how much will the spring compress? So we have the 5 kilogram mass that's gonna slide down the hill, collide into a 10 kilogram mass. In the first scenario where it's perfectly inelastic, they will then stick together and they will slide into the spring. Assume it is an ideal spring. So when I want to figure out how fast the 5 kilogram mass is going when it hits the 10 kilogram mass, what physics concept am I working with? Momentum is really useful if we have a closed system. And as it's falling, we have an external force of Earth. So if we want to use momentum, it's we could, I guess, use impulse. All right, so we've got two scenarios there. If we're going to use momentum without a collision, it's either a closed system, but we do have the Earth involved. So we can bring the Earth into it and figure out how much does the Earth move up as this mass is going down. Or we keep it an open system, in which case we need to deal with impulse is equal to the change in momentum. And impulse is force times time, so we'd have to figure out how much time does it take for the mass to get to the bottom. But I gave you absolutely no specs about that curve, so finding the time is going to be difficult. So momentum is not going to be the simplest way. What other options do we have? Momentum is most convenient when there's a collision or you're given some time of interaction. That's when that becomes most convenient. I wonder if we've done some problem with something sliding down a hill. Let's assume the hill's frictionless, just to make life simpler. Yeah, let's build it in from.
Is it gonna be work?
Keep going along that line of thinking.
Using the kinetic energy, figure how much kinetic energy to build the, and, yeah.
You're saying a number of really nice words. Let's see if we can, someone else want to help them out, string it together?
Are we using non-conservative force? The W,
What are the forces that are going to be acting on this as it slides down the hill? Yeah, I'm gonna nitpick it, sure, I should nitpick this. Say it again properly. So we need to help them out?
Force due to gravity.
There we go, or gravitational force, or, in this case, weight.
Gravitational force.
Oh, you did say it?
Now I was about to.
Oh. I can't just cut you off. All right, so gravitational force is involved, so conservative or non-conservative?
Should be conservative.
It is indeed conservative. What are the other, there is one other force acting on the box as it slides down the hill?
Normal force?
Absolutely. What is the work, back up. Is it conservative or non-conservative?
Conservative.
Ooh. Try again.
Non-conservative.
There we go, yes, exactly. It's indeed non-conservative. But is it doing any work? There we go. It is not doing any work, because the normal force is perpendicular to the movement. Therefore, the only thing doing work is a conservative force, therefore,
I know what it is, but I don't know how to phrase it.
Is it the potential energy is MGH? The potential energy is MGH?
we're gonna get there.
Oh.
I'm looking for a principle first before we get to the specifics.
If it's conservative, the initial energy is gonna equal the final energy.
Okay, otherwise known as,
Conservation of energy.
yes, that's, or energy is conserved, got some flexibility there. All right, so as it goes down, energy is conserved because the only thing doing work is the work done by a conservative force. So, the initial energy equals final energy. I got my two types, got my kinetic plus my potential. Initial is equal to my kinetic final plus my potential final. Got one more chance here. What's the formula for kinetic energy? What's the formula for potential energy?
Which one?
The one associated with the weight. There we go. You're just ahead of your time. So I got 1/2 mv initial squared plus mgh initial equals 1/2 mv final squared plus mgh final. This is the 5 kilogram mass that's going to be sliding down. So I'm going to put a little subscript 5 next to the m. Although ultimately it doesn't matter what the mass of that object is for the first part of this, it matters in the collision, but not here. Are any of these things equal to 0?
Yes.
What is?
Initial speed.
I didn't state that, but that, you read my mind on that one. So initial speed equals 0 meters per second. Not always the case. Anything else equal to 0?
Should we make one of the heights 0?
Which one do you want to make 0?
The last one?
Okay.
The final one?
All right. And the masses can cancel out. They're common factors. And so we are now left with g times the initial height is equal to 1/2 times the final speed squared. And so now we can solve. So my final speed, the speed at the bottom of the hill is 2g, square root of 2gh, which is the square root of 2 times 9.8, let's assume it takes place on Earth, times 15. I know the answer is somewhere between 15 and 9.8, or sorry, and 19.6. So it's gonna be somewhere around 17, 18,
17.146.
what, 146? Now, if this were a test problem, there would be multiple parts. The first part might be how fast is the 5 kilogram mass going at the bottom of the incline. Units?
And so that would be meters per second.
And so it gets to the bottom, it collides into the 10 kilogram mass. Now, when we do the second part, when we do the perfectly elastic collision, this first part still stays the same. The type collision is does not affect how fast the 5 kilogram mass is going when it gets to the bottom. So we now have changed this problem into, I have a 5 kilogram mass going to the right at 17.146 meters per second. Colliding into a 10 kilogram mass, which I probably should state is initially going at 0. And so, in a perfectly inelastic collision, what's going to happen when they collide?
You said inelastic?
Inelastic, perfectly inelastic. What will happen to them?
They're gonna stick together.
Right. So, P initial is equal to P final. Initially, I have 5 times 17.146 plus 10 times 0 is equal to 15 times the final velocity after the collision. This VF here is not the same as that VF there. This VF is just after the, when the 5 kilogram gets to the bottom of the hill. This VF is for after the collision. Or I call this VF1 and VF2, just to differentiate them. Now, what assumption did I make here?
That right is positive.
Absolutely. All right, so I have 5 times 17.146.
Maybe 5.732.
0.732. And so what's my final velocity?
5.715.
5.715.
Meters per, 5.715. And that's meters per second.
So the 5 kilogram comes down, smacks into the 10 kilogram, they now move it together and they hit the spring. So as the spring is being compressed, what physics principle are we working with now? So we did conservation of energy to the bottom, conservation of momentum and the collision, and then we're now at the spring.
Potential energy from the spring.
Okay, so what's the general principle we're talking about here?
Conservation of energy.
Absolutely. So we have conservation of energy once more. The kinetic will be transferred back into potential, this time potential energy from the spring, as Cato said. So, well, that still stays the same, so starting with this point, 1/2 mv initial squared. This VI here is the initial energy, the initial sorry, I'm back. VI is how fast that the 15 kilogram mass is going just before it hits the spring. All right, so now we're dealing with potential energy from a spring. What's the formula for the potential energy associated with a ideal spring?
One-half K times delta X squared.
Initial. 1/2 k times delta x final squared. Anything equal to 0?
Delta X initial.
Because the spring's just sitting there. And, anything else? Looking for maximum compression.
It's gonna be the final velocity then.
Because the maximum compression, that's when the spring stops and it's about to send that whole mass back up. So we have now reduced it down to 1/2 times one mass times the speed just before hitting, which is the 5.715 squared. Is equal to 1/2 times K, which I established, I did do that one at least, 20 times delta X to the final squared. And so now it becomes a math problem. Delta XF equals the square root of or somewhere around 5.
So 4.9497?
4.9497.
9497. That's in, wouldn't that just be,
You said M? Yes, meters. Questions? Yes, Brandon.
How close do you want, answers as far as like if this were a test question? Cause that, she got 4.9497 and I got 9493, so how,
Oh, not, so it's just different by this number right here?
yeah.
Yeah, that tester quiz, that's